And today I will be giving a talk about very interesting topic. So utilizing the hollow specimen method to run some hydrogen testing at elevated temperatures. So we have been seeing from Johan this morning. We did that for austenitic steels up to 100, but now I'm talking about measurements up to 800 degrees. So this is the outline of my presentation. You have seen this slide earlier from Johan. So this is the project that actually we're going to present in the next session as well, part of it. So Johan was like focusing on the storage of transport. I will talk about the automotive, and later on in the next session, my colleague Franz will talk about the results from power generation. A little bit background. So we are all aware about the high potential of hydrogen gas, especially that can be used as a green fuel. It can tremendously lower down the CO2 and NOx emissions. But it can also be used as a fuel for diesel internal combustion engines. But we need to screen out and check the current materials, whether they will work or not under these conditions. So don't take this as a granted. So this is just a preliminary work we did in this project. So we have selected conditions quite severe, very high pressure, and highest possible operation temperature. Digging into the materials. So we are looking into 3 different materials here. It's a lot of information. I won't go through it all, but in principle, we are looking into 3 different applications. So we have the first one, CMO material over there on the beginning. I went with the wrong button, sorry. I'll go back here. Yes. So CMO, ferritic matrix cylindrical graphite nodules application exhaust components. You probably wonder why exhaust. I mean, it won't be with direct contact with hydrogen gas, but still, if the gas it's not fully consumed, some of the hydrogen will pass through the exhaust part. Then we have this compacted graphite iron, maybe similar high carbon content and ferrite matrix, and different type of these graphite particles. And then we have iron nickel base alloy, NCF, gamma prime matrix with different type of precipitates, so meant for high temperature applications. I just want to highlight on this slide, these are the tensile properties done like at room and high temperature, solid specimen. You see the tremendous drop of properties if one does test at 800 degrees. Let's move further. Classically, the same way as we have presented so far from Sefer's side, hollow specimen methodology, coupled with post-mortem measurement of hydrogen to see whether we have some uptake and how this hydrogen is affecting the possible trapping sites, and as well factographic observation. Conditions, SSRT test, running at 3 different temperatures. You can see the temperatures in the table, and 200 bar, argon as inert environment, and hydrogen environment as well. Digging into the first results, so here we have a representative stress strain curves obtained at room temperature, high temperature in argon and hydrogen. And below that, you have the relative properties, namely the yield strength, tensile strength, and the relative elongation compared hydrogen over argon. So what one can conclude from this is that all the properties seems to be affected, but the most severe one is the elongation. And if we do a comparison between the effect of temperature, we do see higher degradation at room temperature compared to high temperature. If we move to the CMO material, so this is what I highlighted, the properties. So at room temperature, we see expected kind of, and high temperature expected results. So the UTS here on this test goes down up to 30 megapascal. When we compare the effect of properties, again, the relative elongation severely affected, maybe slightly better behavior at room temperature. NCF, we don't see any effect on the yield strength. We do see effect on the slight effect on high temperature testing for the tensile strength, but we do see effect as well higher for the relative elongation. Some snapshots from the fructography comparison between temperature, argon and hydrogen. So on the left you have argon and on the right hydrogen. So what can be seen is typically very similar behavior regardless of the type of gas. We have mix of cleavage and quasi-cleavage decohesion. High temperature CGI, namely ductile type of behavior. So we have definitely this McAvoy coalescence mechanism of fracture. And this is actually a first indication that supports the SSRT result. CMO, room temperature, the same here we see on both cases, regardless of the gas, quasi-cleavage decohesion. High temperature, we see a sponge fracture. I don't know how to define this because here we have extremely high temperatures, so we assume that we might have also effect of high temperature hydrogen attack that can result in this. But nevertheless, what is interesting is that in hydrogen gas conditions, we have also vertical cracks, which are kind of strange, but non-expected. And this is also related maybe to cracking of the material due to hoop stress, which is probably close to the strength of the material. NCF comparison, room temperature, microvoid coalescence, ductile type of failure. High temperature, mix of intergranular type of fracture all over the surface for both type of gases, argon and hydrogen. So in principle, this is probably typical mechanism at elevated temperature. It's not really related to hydrogen. And also some ductile areas. Digging into the hydrogen effect. So if we look into the CGI, here on this slide, you can see on top the TDMS spectra that describe reference material, which has not been tested. And the black and the red curve represent measurement of hydrogen after room and high temperature SRT testing. So you can see definitely a different distribution of hydrogen affecting at room temperature, namely weak trapping sites, and as well at high temperature, strong trapping sites. If you look into the content levels that we measured, rather logical. So we see uptake, but the main difference is which sites we occupy. And this also supports the SSRT measurements. CMO, not high effect on room temperature in terms of uptake. So the curves quite match with the reference measurement. On the other side, we have the high temperature where we do see an uptake, and that is, of course, expected. As well, the same, similar to NCF material. So, namely, the high temperature test resulted in only strongly trapped hydrogen uptake. I dig into conclusions. So, CGI, mainly used for cylindrical head applications. It seems that it's more sensitive at room temperature than high temperature. Hydrogen uptake we measured at both testing conditions in terms of temperature, but we see a different distribution of hydrogen. We saw also brittle fracture at room temperature and ductile fracture at high temperature. CMO material, significant loss of properties, ductility at room and high temperature. You can just see the numbers there, how much we have reduced the ductility the leakage, the elongation to leakage. At high temperature, this material was very sensitive. I already explained our assumptions. We saw a brittle fracture mode for both argon and hydrogen at room temperature, and sponge-like, you can see this vertical crack on the slide at high temperature. And at room temperature, we didn't see any uptake, but notable uptake of hydrogen at high temperature. Nickel base, significant loss in ductility, moderate loss in strength. You can see the numbers. Relative properties indicate that it's not sensitive, although some of the elongation is lower at high temperature compared to the room temperature. And we do see a ductile fracture at room temperature and intergranular brittle with some mixed ductile brittle regions at high temperature in both type of gaseous exposures. And similar as CMO, we don't see uptake at room, but strongly trapped hydrogen uptake at high temperature. Just again, general remarks. I think it's very reasonable to conclude. We have seen many hollow specimen presentations this week, and I would just conclude the same. It is a possible good tool for screening the behavior of metallic materials in high pressure gas, but unfortunately, in this case, didn't work well for CMO. And results from this study, they show that we need further testing to justify whether these type of materials are suitable for this type of applications. One of the ways is to do more SRT testing in different conditions or pressure temperature regimes in argon and hydrogen, but also as seen for the first time, at least me from Sunday, from Greece, to check the effect of oxygen, and that's on the pipe. So we do that work currently. In addition to that, it's very important also to check the fatigue properties in order to capture better the service conditions. And I would like to acknowledge only our national financing agency, Vinnova, for supporting this project, and our partners in this work package of the project, Scania and Volvo. Thank you very much for your attention.